Okay, class, welcome to lecture 10. So today we are talking about probability density functions, a very fancy sounding concept, but I'll warn you that there's going to be lots of other very fancy sounding words in this lecture, but hopefully that won't overwhelm you. And then this specific phrase or term probability density function will not come in until much later. Okay, but to get there, we're going to first think about this sort of issue or problem with the stuff that we've been doing. So far, we've learned about probability, and specifically, we've learned that probability of an event, we should think about it as the number of ways that event can happen. So like the probability of rolling a 5 or something is how many ways you can roll a 5 divided by the total number of possible outcomes. So that's all good for the stuff we've been doing. And to be very technical, the idea is that this is working for something called a discrete random variable. And I don't want you to get too caught up on this fancy terminology. But the basic idea is that this works, meaning this idea works for situations where outcomes are finite versus not finite. So meaning in cases or situations where the number of outcomes is finite. So like when you roll a dice, there's only 6 outcomes. When you flip a coin, there's only 2. It's some finite number of outcomes possible. Or if you pick a card, there's 52. And so the reason that this works is because you can divide by a finite number. I can divide by 12, I can divide by 6, I can divide by 2, I can divide by 52, whatever the number is, I can divide by it. And so don't worry so much about this term here, but instead just think about how in the case where our events have a finite number of outcomes, it makes sense to do this. So what about when it's not finite? Well, what happens is we call that situation continuous as opposed to discrete. So one way to say this is, what about continuous random variables? So that means, as opposed to discrete, there can be infinitely many outcomes. That's what we want to think about next. So the idea is, I cannot divide by infinity, so we run into trouble. Infinity is not an actual number, so I can't divide by it. So our little way of thinking doesn't work. Okay, so that's what we want to think about. This formula here, I can't just put infinity down there underneath. It's not going to do anything. Okay, so first let's think about what are these types of situations. So you might think like, oh wow, it must be super complicated because it's infinite as opposed to like rolling a dice, which only has 6 outcomes. Well, no, you don't have to go that. It's not that bad. It's nothing too unfamiliar. It's just stuff that you maybe have not have thought about in a probability way. So here's an example. The speed of a car, if I ask the question correctly, I can say that the speed of the car is a continuous random variable. Because depending on how precise you want to measure the speed, there are infinitely many possible outcomes. So this is, again, because there can be infinitely many possible outcomes, depending on how precisely you measure. So for example, I could be going 30 miles an hour, but maybe I'm actually going 30.123 miles per hour. Or I could be going 30.1237109 miles per hour. So there's infinitely many speeds I could be going. I don't just go 30 or 31 or 32 and then I stop. I can go between all those, between 30 and 31 in infinitely many different ways. So for example, in our previous way of thinking, if somehow there were like, say 10 ways to go 30.123 miles per hour, then you might want to say that the probability of doing this would be 10, because there's 10 ways to do that, over what? Well, there's infinitely many different speeds I could be going, so there's infinitely different outcomes. So what the hell is this? Well, it's nothing. So this is the issue. So another example is basically anything to do with time, depending again on how precisely you measure the time. So maybe the amount of time to do something, to do a task or something. So it could take 15 minutes maybe, or 15.1 minutes, or 15.11 minutes. There's just infinitely many different amounts of time that it could take. So same issue arises. Okay, so that's one problem with trying to calculate probabilities like we're used to for continuous random variables, meaning situations where there's infinitely many things that could happen. But another problem is just the way we display it. You cannot use those charts just for the same sort of reason. So we cannot use the charts to show a distribution of such a random variable. So the point of these charts here is you're saying what your random variable can be here on the left, and then on the right, you're assigning probabilities to those things. But now, little x will have infinitely many options. So this chart will never stop. It'll just go down forever. We don't want that. So that's just another issue with trying to try to create a probability distribution for a continuous random variable the same way we did before. It's just not going to work. And this is another reason. So for example, if you were doing the speed of a car, you might say that the car speed is the random variable, capital X. So then the possible car speeds would be little x, and then it would just be infinitely many different things. And you would never be able to stop writing. could be any speed. And there's infinite possibilities. Okay, so that's the problem. So now you might think, oh, how do we fix that? It's impossible. It's too much. Infinity is too big of a problem. Just a puny human. Well, it's not so bad. We can do it. Okay, so how do we do it? To fix these issues, the secret to math is don't fix the issues. Instead, change the question. This solves everything. Question's too hard, don't do it. Change the question. Sometimes people do this on exams on accident, and they should not do that because those questions are doable. Okay, so instead of asking things like we have been asking, that's where the problem really lies. So instead of asking like what's the probability of driving exactly, I don't know, 30.25 miles per hour. So this is the kind of question you might have asked before. Like, what's the probability of rolling a 5? Same type of question. This is the question that's breaking our ability to continue. So we're going to change it. So instead of this, we ask better questions. Things like this. It's a very subtle change. What's the probability of driving? The keyword here is going to be between 30 and 35 miles per hour. That's the new question, and that's the better question that we can figure out how to deal with. So how do we deal with this type of question? Well, we don't use charts anymore to display probabilities. We are going to use graphs. So then to decide the answer, we can use a graph. By graph, I mean graph that you learned about in other math classes. A graph that maybe could look like lots of different things, but this is just some random example I've just created. This is a graph of a function. So I'll try not to use the word function too much to scare you, but just a graph like this. And maybe it starts somewhere and goes somewhere else. Maybe it goes from 20 to 90. And then the idea is that area under the graph, so if this is 30 and this is 35, the area under the graph is going to be the probability. So the key is to thinking of area as probability. This is not so strange. We did this when we created Venn diagrams. We sort of thought about it the same way. And that's going to be the key. So let me finish writing that down. So, and we use the area under the graph as the probability of being in an interval. So in that situation up there, from 30 to 35 miles per hour. So then the probability of being the car being between these two speeds is the shaded area above that I drew up here. So however much area that is, that's the probability. So then like, I could just do a different question. So I could say like, what's the probability of being, so this is the types of questions we'll ask now, being between say 35 and 90, that would just be all of this area, 35 to 90. Or I could say, what's the probability of being between 20 and 35? That would be this red area. That's the idea. So the key is that you're looking at the area under the graph between the two numbers that you ask the question about. So then different choices of graphs distribute, hence the word distribute for distributions, distribute the probability differently. So the different choices of graphs distribute. The idea is that the graph is distributing the probabilities differently. So for example, there was that graph I wrote up there, but here's another graph. It's going to go from 0 to 30, and it's just going to be a straight line at the y value, the height, 1 over 30. So then, for example, the probability of being between 15 and 20 is this area here, which I can actually calculate because it's a rectangular shape. So I know how to calculate the area of a rectangle. So here. So this could reference a car still or some other situation, but could reference whatever you're dealing with. So here the probability of being between 15 and 20 is given by the area of the shaded region, because it's just the area under the graph between those two numbers. And I know how to calculate the area of a rectangle. It's the height times the width. So what's the height here? Well, it's 1 over 30th, because that's how high up it is to this line from 0. And the width from here to here is 5, because it's 20 minus 15. So the area of the rectangle, I'll call it capital A, is 1 over 30 times 5, aka 5 over 30, which you can reduce if you want. But that's the probability that this graph has distributed to the random variable. It's a very fancy way to say it. Distributed to random variable. Is, I'm not really saying this correctly, but whatever, of being between, this could be said a little bit better. But the idea is that the graph is distributing the probability to the random variable x, and it's saying that the random variable x has a probability of 5 over 30, that's what this is, of being between 15 and 20. And that x is just going between 0 and 30 total. Okay, so we could do another little mini example. So what if I did from, here's another color. So if I do from 5 to 20, then I'm looking at this blue area, and I could say that the probability of the random variable x being between 5 and 20 is this blue area, which has height still 1/30th, and now the width is going to be 15, because it's 20 minus 5. So it's 15 times 1 over 30, or the other way, however you want to say it, 15 over 30. So this random variable has a 50% chance of being between 5 and 20. Okay. So this type of graph, that a straight line graph, does have a fancy name, but I think I'm going to leave it out so as to not confuse extra, because there's more fancy names coming. But in the notes that I'll post, the fancy name will be there. Okay. So I'll skip that fancy name and instead jump to the next fancy name. So in general, what these things are called, they are called probability density functions. I am not a professional statistician. I am a mathematician. So unfortunately, I don't know how statisticians pick names, but they seem to do a terrible job. Because I don't know. I don't like this name. But anyway, people call it, they call them PDFs for short. Someday I'll go learn about these names. So then what are PDFs? Well, they're kind of like these, except more general. But the key thing to notice is what's the total area of this picture that I drew here? I didn't just draw this picture in this way for no reason. The total area is, well, it's 30 across and it's 1/30th high, 30 over 30, that's 1. So remember, the probability of anything happening should be 1 because something has to happen. So there's a 100% chance that something happens. So that rule is going to apply to these guys too. So a PDF is a graph like this, but it could be a much fancier graph. But what you need is you need the total area to be 1. That way you are modeling a situation where probability is involved, because the probability of something happening better be the 1, which should be the total area. And then the graph has to always be positive, or it could be 0. So as long as you obey these 2 rules, you count as a PDF, probability density function. And that D, the letter D is confusing because you always want to say distribution or something, because we've been saying the word distribution a million times. But no, probability density function. Okay, so here are some other examples that are different than just having straight lines. Well, this is still a straight line, but it's not straight across at least. So this is a PDF because the total area underneath it is 1. And the graph is not ever below the x-axis, so it's not negative ever, which is what we want. But first, let's check that the total area is 1. So I got to remember the area of a triangle is 1/2 times the base length. So the base is 2 times the height of this triangle. That's just 1. So that equals 1. So that's what I want for it to be a PDF. Good. So the graph is never negative. aka it's never below the x-axis. So now I could calculate probabilities. So here, if I have a random variable x, I could say that the probability of it being between, say, 0 and 1 is this area. So that shaded area is, well, it's still a triangle. That's the nice part. Still a right triangle. So I can figure out its area by doing 1/2 times the base. So the base of that triangle is just 1 times the height of that triangle. That's just 1/2. So I get 1/2 times 1/2 is 1/4. So that's what I can do. So you'll notice I have to have very particular shapes to calculate areas, because you only ever learned how to calculate areas of nice shapes like rectangles and triangles, unless you've taken calculus. Then you could do fancier stuff. What about this area? So what's the probability of being between 1 and 2? Well, you might think, well, that's not exactly a triangle, so how the heck could I figure that area out? Well, there's several different ways. I could break it up into 2 pieces. So I could break it up into this triangle, calculate that area, add it to this one, this rectangle, and that would be fine too. Or I could notice something else. So the probability of being between 1 and 2 is, well, the total area is 1. This guy is 1. So that means if I just do 1, take away this smaller triangle that I already know is a fourth area, oops, a fourth, that will give me the rest of the area, which is 3/4. So that's taking advantage of the fact that we know the total area has to be 1, just to make our lives a little bit easier to calculate things. Okay, but you can also calculate it manually the way I suggested before. Okay, so notice that the area it's not the same. Those are not the same number, even though the intervals are the same size. So the distance from here to here is 1. The distance from here to here is still 1. So being between 0 and 1, being between 1 and 2 is not the same probability. Okay. So here's another example of a PDF. This is more like the first example I did. So if I make this be 2 and I make this be a half, then the total area is 1. It'll be 2 because it's a rectangle times a half equals 1. So that's a PDF. Here's another one, slightly weirder. You'll notice I have to always make use of triangles and rectangles though, so that you can calculate the area. So here's a more interesting PDF. This will be 1, this will be 2. Okay, that's not very proportional, but, and then this will be 3. Pretend I'm better at drawing. Okay, this height will be a half. So this total area will be 1 because I can just add areas up together to figure that out. So the area of this triangle is 1/2 times the base length, which is 1, times the height, which is 1. That gets me a fourth. Okay, the area of this red piece, it looks giant because I've drawn it badly, but this distance is 1 across, and it's a rectangle, so it's 1 base times height, 1 times a half. So a half. And then this triangle here, well, luckily I've drawn it symmetrically, but you can still see that the distance from here to here is 1. So it's a triangle, 1/2 the base times the height of the triangle is still half. So I get 1/2 times 1/2 is 1/4. And luckily these add up to 1. So this is still a PDF. Okay. So then we could do problems using PDFs, which is just the same thing I've been doing. It was just calculating areas, but now I'm going to put some words in it. So suppose X is a continuous random variable, which is the speed of a car. Whoops, just one A is fine. Suppose that it has a PDF, probability density function, given by this graph here. So I'll give a weirder graph this time. So this car is weird. It goes pretty slow. It only goes 1/2 mile an hour. Sorry, that's not what that 1/2 means. That's what this 1/2 means. So it goes from 0 to 1/2 miles per hour sometimes. Then it goes from 1/2 to 1 sometimes, and then it goes from 1 to 2 sometimes. And the graph is going to jump So it's going to look like this. It's not going to be connected. And then down here will be a little triangle. So first, let's verify that it's a PDF before trying to ask other questions about it. So the total area should be, it's going to be this plus this area plus this triangle area. So the left one is a rectangle, base times height is a half times a half. The middle area is still a rectangle, and it's a half across, half base, but the height is 1, because it goes all the way up there. And now the third part is a triangle, so you do 1/2 the base. The base is 1 times the height is only a half. So you get a fourth plus a half plus a fourth, which is 1. Good. So then you might ask questions like, find the probability that the car is, I don't know, between 1 and 2 miles per hour. That would just be this area here, which luckily I already calculated. It's just this piece, so it's a fourth. Or you might ask, what's the probability it's between 0 and 1? Car is between 0 and 1 miles per hour. That would be all of the area from 0 to 1, all of the area from here to there. So it looks a little bit more complicated, but we actually figured that out. So it's this one plus this one, which was just these two. So it's a fourth plus a half, which is 3/4. Okay. So there's lots more examples. Maybe I'm getting tired, but I'll put one more up if you want to do it for practice. So maybe instead of speed, we'll do time. So X could be maybe the time it takes to do homework. And it has a PDF given by, so it's got to be a graph with area 1. So maybe it'll just be a little triangle that goes over to 4, and it goes up to a half. So you can verify that the total area is 1, but now the units are in like hours or something instead of speed. So that's really what the x-axis is in. I guess I should have mentioned up here that the x-axis was in terms of miles per hour. So then you could say, like, what's the probability it takes between 2 and 4 hours to finish your homework? That would be this area, because it's a triangle-ish type shape. You can figure it out. So I think I'm tired. So you can do that if you want extra practice. You could do problems for this one. Probability of taking between 2 and 4 hours to do homework. That would be this shaded region, this shaded area. But what I do want to mention is in reality, PDFs often have more fancy shapes, and that's what we're going to talk about next time. Something like this, a bell curve. And I don't know if you know, but calculating area between here and here, whatever the numbers that happen to be, is a little bit harder because it's not a straight line. It's very curvy. So you actually need calculus to do the tougher stuff. But luckily, other people did the calculus for us, so we're not going to have to redo it. We're just going to use what they did. Okay, so that's it for this lecture. See you next time.